Hello, bonjour, Dieduit, hey. Welcome to the fourth week of Statistical Mechanics, Algorithms and Computations from the Physics Department of École Normale Supérieure. This week, we will advance our understanding along two directions. From the physical point of view, we have so far thoroughly studied the first pillar of statistical mechanics, the equiprobability principle. Time has come to consider the second pillar, which comes from the Maxwell distribution of velocities and gives the Boltzmann distribution of energies. This second pillar will allow us to heal the dissymmetries between the molecular dynamics simulation, that is the solution of Newton's equations of motion, and the Monte Carlo approach. So far, the molecular dynamics had velocities and positions, whereas the Monte Carlo only had the positions. What we learn today will allow us to overcome the dissymmetry between molecular dynamics and Monte Carlo. To get there, we must deepen our understanding of sampling. And this is the second direction along which we will advance this week. So far, sampling meant that we threw pebbles, placed disks, or fixed clothespins on a washing line. Now, we will connect this sampling problem with the underlying process of integration. The sampling problem will accompany us also in this week's tutorial, Tutorial 4. We will start with the very simple Saturday night problem. On your free evening, you have many options and you can give them probabilities. You can go out with friends, see your family, do homework, do sports. All of these options have statistical weights. And you may think at first sight that the problem is writing down these statistical weights. But it isn't. The difficult part is doing the sampling. In Tutorial 4, you will learn how to sample this distribution along different approaches. And how to do it if you not only have 4 or 5 options, but thousands, millions or billions. How to sample such a discrete distribution efficiently or even optimally, and how to take the continuum limit. All of this are central subjects of daily life at work or study, but as you see, also for the nightlife. In this week's homework session 4, you will be concerned again with the connection between sampling and integration. In fact, you will compute the volume of a sphere, not in 3 dimensions like here, but in 100 or 200 dimensions. This is what Monte Carlo methods are really good for. You will learn for yourself how the sampling approach really goes at top speed in high dimensions and how you can evaluate an integral there. You see, there are lots of exciting developments in week 4 of our course, so let's get started. As we just mentioned, time has come to connect sampling to integration. Let us look back at the children's game. Pi over 4 came out as the ratio of the volume of the circle to the volume of the square. More precisely, we find that the number of hits divided by the number of trials is approximately equal to a ratio of two integrals. The integral over dx and dy on the square of O of x and y times pi of x and y divided by the integral over the square of pi of x and y. In this equation, O of x and y is the function, an observable, and it is 1 inside the circle and 0 outside. And pi of x and y is the uniform probability distribution on the square. By throwing pebbles, we in fact compute the integral dx dy pi of x and y. But notice, on the left side, the probability distribution pi of x and y is absent. It is the samples I that are drawn from this distribution. Furthermore, the dimension of the integral, the fact that the integral on the right is dx dy in 2 dimensions, does not appear on the left. There are no multiple sums along all dimensions. This explains why Monte Carlo methods, sampling methods, excel in high dimensions. For integrals, we have substitution rules, changes of variables. And we will next see how these changes of variables relate to the sampling approach. Our example will be the Gaussian integral. Integral from minus infinity to infinity dx over square root of 2 pi e to the minus x squared over 2. The value of this integral is I equals to 1. And to show it, generations of students have learned to square the integral. So we write I squared is equal to the integral in x times the integral in y. Now let's do a first substitution. We go from x and y to r and phi. X equals to r times cos phi and y equals to r times sin phi. This gives the following integral. Now we do a second substitution from r to psi. And then finally we do a substitution from exponential of minus psi to upsilon. And we arrive at the formula I squared is equal to the integral from 0 to 2 pi d phi over 2 pi times the integral from 0 to 1 d upsilon. We can do these two integrals and confirm that I squared is equal to 1, which means that I is equal to 1. We have computed the Gaussian integral. But in fact, we don't care about the value of this integral. What we do is we use our relationship between integration and sampling. So we can see that phi, in fact, is a random number between 0 and 2 pi. And upsilon is a random number between 0 and 1. So now let's take a little crab's walk back from the variables phi and upsilon, or from the samples phi and upsilon, back to x and y. So the samples phi and upsilon give samples phi and psi, phi and r, and finally x and y. Let us discuss this as what it really is, namely an algorithm, Gauss test.py. Its graphics version, Gauss test movie.py, allows you to see that the flat input distributions of phi and upsilon get transformed into distributions of x and y that are Gaussians. So we have a distribution e to the minus x squared over 2 and a distribution e to the minus y squared over 2, and the two are independent. So what you see here allows you to understand that the substitution rules, the changes of variables in integrals, also apply to the samples. Before going on, please take a moment to download, run and modify the programs we just discussed. On the Coursera website, you'll find the program GaussTest.py. Understand that phi and epsilon are numbers, samples, and that these samples are transformed into numbers, samples of x and y, taken from a Gaussian distribution. Take the program apart. In the graphics versions of GaussTest.py, you see the variable epsilon. It's a uniform distribution between 0 and 1. Check that it is actually uniform. Then there is an intermediate variable psi, minus logarithm of epsilon. What is its distribution? Check it out and compare it to the analytical calculations we did a few minutes ago. Now let us consider vectors or lists of Gaussians, not just a single one. We start in 2 dimensions with x and y, 2 independent Gaussians. This is shown here in this program, and note that we have gone from our homegrown version GaussTest.py to the Python version random.gauss. It uses basically the same algorithm called the Box-Müller method. Output of Gauss 2D movie.py is shown here. You see a first sample, a second sample, a third sample, and so on. What you see is a cloud of points. Each point is an independent Gaussian in x and an independent Gaussian in y. And note that the distribution, the cloud, is isotropic. It is invariant under rotations. This situation is unique. It is only Gaussians that can do it. Remember that we already had distribution of x and y in the children's game. It was a square and it changed shape when it was rotated. To understand why this distribution is isotropic, let's look at our program GaussTest.py. You see that there is a variable phi, which is uniform between 0 and 2 pi, and the point xy is oriented along this axis. Another choice of phi would simply rotate the point xy along the origin. You can directly check this also in our little crab walk we took a few minutes ago. You see, we arrived from independent distribution x and y at a distribution integral from 0 to 2 pi d phi over 2 pi times an integral in r. There is no function depending on phi, which means that the variable phi is independent. We will considerably deepen this and generalize this for higher dimensions in a few minutes. Gaussians are unique in that independent distributions in x and y give an isotropic distribution in 2 dimensions. This property is general for Gaussians in any dimension. The 3-dimensional case is shown here in Gauss 3D.py. Each point is a vector x, y and z, and all 3 are independent Gaussians. So output of the movie version is shown here. 1 point, 2 point, 3 point, and so on, many points. You see that the distribution is isotropic. And in the movie version, we can even turn around the distribution and look at it from all angles. Does this make us more adventurous? Yes, of course. Let's give this distribution a haircut. Let's take each point x, y, z and renormalize it to 1. So we take x, y, z, independent Gaussians, and divide this vector by the square root of x squared plus y squared plus z squared. So now we have random points on the unit sphere. And as the distribution initially was isotropic, it remains isotropic on the unit sphere. So we found an algorithm to put random pebbles onto the surface of the sphere. Understand that isotropy does not simply mean that the points are on the surface of the sphere. They are so by construction because we renormalized each point x, y, and z to have a radius equal to 1. Isotropy means that the distribution of points, the probabilities distribution, is uniform on the surface of the sphere. So here is the program directSurface.py in general dimensions. It puts points randomly with a uniform distribution on the surface of the hypersphere in d dimensions. Now let us follow mathematically what is going on. We have to use the concept of sample transformation. Remember, sample transformation means that the changes of variables in the integral applied directly to the samples. So the integral that we are concerned with is the integral dx0, dx1, and so on, dx d minus 1, exponential of minus x0 square, exponential minus x1 square, exponential minus x d minus 1 square. Now let's do a change of variables from x0, x1, and so on, x d minus 1 to r, the radius variable, and an angular variable, omega, the solid angle. Integrated over the whole space, d omega gives 2 pi in 2 dimensions and 4 pi in 3 dimensions. So now see that the integrand depends only on r. It is equal to exponential of minus r squared over 2. And the differential dx0, dx1, and so on, dx d minus 1 yields r to the d minus 1 d omega. So for our d Gaussians, we end up with the distribution or the integral dr r to the d minus 1 exponential minus r squared over 2 integral over d omega. It is 2 independent integrals, one in r, one in omega. There is no function depending on omega, which shows that we are isotropic in angles on the surface of the sphere in d dimensions. Finally, let's do a trick. Let's renormalize the radius r to be on the surface, r equals to 1, and then blow it up again to have a distribution pi of r equals to r to the d minus 1 dr between 0 and 1, rather than r to the d minus 1 exponential minus r squared over 2 from 0 to infinity. What we obtain is written in this program, directSphere3D.py, and it is a random point inside the three-dimensional unit sphere. So output is shown here, 1 point, 2 points, 3 points, many points, and we can turn it around, and we have a random point inside the surface of the three-dimensional sphere. There is also a general program that allows you to sample a random point inside the d-dimensional hypersphere. Before continuing, please take a moment to download, run and modify the programs we discussed in this section. That means take them apart and put them back together. On the Coursera website, you will find the program directsphere3d.py and directsurface3d.py. These programs, these short and sweet programs, are marvelous, and they should have their place in the national museums all over the world. Molecular dynamics concerns positions and velocities, whereas the Monte Carlo method considers only the positions. Why the velocities disappear from our Monte Carlo program and how we can make them come back deserves a most thorough answer. To incorporate velocities into statistical mechanics, we again use the equiprobability principle. For hard disks in a box, during an event-driven molecular dynamics simulation, the energy is equal to the kinetic energy, and it is fixed. Kinetic energy is equal to 1/2 m sum over the velocity square, v0 square plus v1 square, and so on, plus vn-1 square. In this equation, each velocity has two components. v0 equals to v0x, v0y. So that the square v0 square is equal to vx0 square plus vy0 square. In this equation, you see that the sum over the squares is fixed. Just like on a circle or on the surface of a sphere, only in higher dimensions. Any legal set of velocities is a point on the 2n dimensional hypersphere of radius square root of twice the kinetic energy divided by the mass. For 4 particles in a box, this forms a vector of 8 components, an 8-dimensional vector on the surface of the 8-dimensional hypersphere. The equiprobability principle applied to these velocities means that the statistical weight pi of v0, v1, and so on until vn-1 must be a constant if the vector v0 until vn-1 is on the surface of this hypersphere and 0 otherwise. This means that the set of velocities is a random vector on the surface of the 2n-dimensional hypersphere. Fortunately, we just became experts in the subject of sampling a random point on the surface of a hypersphere using 2n independent Gaussian random numbers. Remember that the algorithm directSurface.py involved a rescaling of velocities, but that this rescaling became unnecessary in high dimension if the variance of the Gaussian was chosen correctly. In our case, we have to choose each component Vx or Vy according to a probability pi of Vx proportional to exponential minus Vx square divided by 2 sigma square, where sigma is given by the square root of 2 over m kinetic energy divided by 2n. Or, more generally, in d dimensions rather than in 2 dimensions, given by the square root of 2 over m kinetic energy divided by dn. Look here at the distribution of the radius r in the algorithm direct surface dot pi before rescaling, and see that it becomes sharper and sharper with increasing particle number right at the correct value. This means that each velocity component is a Gaussian random number. This is the Maxwell distribution. It is really famous, yet we have derived it by ourselves. The total kinetic energy divided by dn is the mean energy per degree of freedom, and it is equal to 1/2 kb times T, where T is the temperature in Kelvin and kb is the famous Boltzmann constant. We find that the variance sigma square of the Gaussian describing the velocity distribution in our system is given by sigma square equals to kbt divided by m. And we finally arrive at the probability distribution of each velocity component of each particle, pi of v, proportional to e to the minus v square. Now remember that the velocity of each particle was given as v equal to vx vy. So the velocity distribution of the absolute value of the velocity is given by probability distribution pi of v proportional to v exponential minus v square, because the volume element dvx dvy can be written as 2 pi v dv. In 3 dimensions, we do the same thing with vx, vy, vz. The probability distribution for each component is unchanged. It is a Gaussian. But the probability distribution of the absolute value of the velocity is now proportional to v square e to the minus v square, as shown here. We can compare the Maxwell distribution that we just derived with the simulation results obtained by event_disk_box.py in the second week, and check that the histogram of each velocity component of an individual particle is a Gaussian. The probability distribution is like e to the minus v square. Furthermore, we can check that the probability distribution of the absolute value of the velocity of each particle is also given by a Gaussian v times exponential v square. So we find that in order to introduce velocities into the Monte Carlo scheme, we have to sample independently from the particle positions the velocities from a Gaussian with some rescaling. We thus establish the complete symmetry between the molecular dynamics approach and the Monte Carlo sampling approach. So finally, let us look again at the Maxwell distribution, which has the form exponential of minus energy divided by kBt. This is for one particle and one component only. But it also applies to a subsystem of particles inside a larger simulation box. For example, cut off by boxes that allow exchange of energy and of momentum. Such a subsystem has energy E that may vary, and the probability distribution is pi of e is proportional to exponential minus e divided by kbt. We have arrived at the Boltzmann distribution, the second pillar of statistical mechanics, and we have done it all by ourselves. In conclusion, we have studied in this fourth lecture of statistical mechanics, algorithms and computation, the intricate relationship between sampling and integration. The changes of variables in integration was mirrored in the process of sample transformation. The most important such change of variables, or the most important sample transformation, appeared in multi-dimensions from Gaussians to an isotropic distribution. This magnificent relationship between Gaussians and isotropic distributions was very well understood by the founders of statistical mechanics, and it produced the Maxwell distribution and, by generalization, the Boltzmann distribution. It is now time for you to study the simple programs that come with this lecture. The math is simple and the concepts are clear, yet the implications are far-reaching. What we discussed here will be considerably deepened in this week's tutorial and homework session. Next week, we'll take our first step into the field of quantum physics and quantum statistical mechanics. In the meantime, have fun with tutorial 4 and homework session 4. And see you again next week at Statistical Mechanics, Algorithms and Computation.